Welcome back. Are you preparing for job interview intake or want to deepen your understanding in algorithm analysis? If so, you are in the right place. Today we are diving into a crucial topic, asymptotic notation. Imagine this. You have just been asked to optimize an algorithm during an interview. How do you explain its efficiency? That's where asymptotic notations comes in. Why does this matter? In the fast-paced world of computer science and programming, knowing how to express the efficiency of algorithms in terms of time and space complexity can set you apart. So, whether you are looking to impress in an interview or deepen your understanding of algorithm performance, this topic is for you. Let's explore how we can express the time and space complexity using an asymptotic notation. Simply put, asymptotic notations allows us to describe the behavior of functions as the input size approaches to infinity. It helps us to compare algorithms based on their efficiency, making it a crucial tool in algorithm analysis. Let's look at the key types of asymptotic notations that we'll be focusing on today. We have three prime types of asymptotic notation that we use to describe an algorithm. First, we have big O notation, which is represented using a Greek letter, capital O. Next is big omega notation, represented by the Greek letter omega. And finally, we have a big theta notation, represented by the Greek letter theta. First, let's discuss about big O notation, which is represented using the Greek letter big O. This notation signifies an upper bound on the growth rate of function, helping us to understand the worst-case scenario of an algorithm's performance. Big O notation is particularly useful for estimating the maximum resource we might need at the size of input growth. This helps us to make informed decisions about the efficiency and scalability of an algorithms. Let's look at a mathematical expression for big O notation. F of n equal to big O of g of n if there exists a constant c greater than 0 and n0 greater than or equal to 0 such that f of n is less than or equal to some constant c multiplied by g of n for all n greater than or equal to n0. Let's explore a mathematical expression one by one. The expression n not greater than or equal to 0 indicates that n0 is a non-negative constant. This value serves as a threshold, marking the point beyond which we analyze the behavior of the function f of n. In simpler terms, n0 represents the smallest input size for which the asymptotic relationship holds true. It must be 0 or a positive integer, ensuring that our analysis is valid for non-negative input size. When we say such that, we are establishing a condition that must be satisfied for all n that are greater than or equal to n0. Specifically, we are indicating that for this value of n, f of n is less than or equal to some constant c times g of n. This means that starting from n0, for all larger value of n, the function f of n will not grow faster than g of n, multiplied by some constant. In this expression, c is a positive constant that scales g of n. This framework allows us to analyze the worst-case performance of algorithms, providing a clear picture of their efficiency and scalability. Now, let's explore some concrete examples of functions analyzed using big O notation. The first example is linear function. Consider the function f of n equal to 4n plus 3. In this case, the dominant term is 4. As n grows larger, the 3 becomes negligible. Therefore, we express this function as f of n equal to big O of n. This indicates that the growth rate of f of n is linear, which means the function grows proportional to the input size. Next, let's look at a quadratic function. F of n equal to 3n cubed plus n squared plus n plus a constant 20. Here, the dominant term is 3n cubed. For larger value of n, the lower order terms n squared, n and the constant 20 do not significantly affect the growth rate. Thus, we can express this function as f of n equal to big O of n cubed. This indicates that the growth rate of f of n is cubic, which means the maximum time or the worst case time taken by this function is cubic time. Finally, let's examine an exponential function. f of n equal to 3 the power of n plus constant 2. In this scenario, the dominant term is 3 the power of n. As n increases, the constant 2 become insignificant. Therefore, we express this function as f of n equal to big O of 3 the power of n. This shows that the growth rate of f of n is exponential. This example illustrates how we can use big O notation to classify the growth rate of different functions, helping us to understand their efficiency and scalability as the input size increases. If you want more clarification on how growth rate scales with input size, be sure to check my lecture video on class of time function. Now, let's look at our first example to compare the growth rate of two functions. F of n equal to 4n plus 3 and g of n equal to 3n cubed plus n squared plus n plus 20. First, we have f of n equal to 4n plus 3, which is a linear function. This means its growth rate is proportional to the input size n. Next, we have g of n equal to 3n cubed plus n squared plus n plus a constant 20, which is cubic function. This function grows much faster than linear function as n increases. Now, let's identify the dominant terms in each function. For f of n, the dominant term is clearly 4n. As n becomes large, the plus 3 becomes insignificant. For g of n, the dominant term is 3n cubed. The other terms n squared, n and the constant 20 will have less impact on the growth rate as n gets larger. Let's express this function using big O notation. For f of n, we can say f of n equal to big O of n, which is a linear time. This indicates that f of n exhibits linear growth. For g of n, we have g of n equal to big O of n cubed. This tells us that g of n grows cubically, which is significantly faster than the linear growth rate. Now, let's compare the growth rate of these two functions. Since n cubed grows faster than n, as n increases, we can express that relationship as f of n equal to big O of g of n. Because from the mathematical formula, if the growth rate of function f of n less than or equal to some constant c times g of n, we can express it as f of n equal to big O of g of n. This means that the function f of n which grows linearly is bounded above by g of n, the cubic function. Essentially, for very large value of n, g of n will outpace f of n. Let me add one more example to further illustrate the concept of big O notation. In this example, we'll analyze the following two functions. The first function f of n equal to n cubed plus 7n squared plus n, which is a cubic function. And the second example, g of n equal to 3n plus 5n, which is linear function. In the first step, let's start by identifying the dominant term in each function. For f of n, the dominant term is n cubed. This means that as n grows larger, the 7n squared, n and any constant terms become less significant. For g of n, the dominant term is 8n, since 3n plus 5n is equal to 8n. This indicates that g of n grows linearly. In the second step, let's express this function in big O notation. For f of n, we can say that f of n equal to big O of n cubed. This tells that the growth rate of f of n is cubic, which is quite significant as n increases. For g of n equal to big O of n. This indicates that g of n grows linearly, which is slower compared to the cubic growth rate. Finally, let's compare the growth rate of these two functions. Since n cubed grows faster than n, for larger value of n, we can express this relationship as g of n equal to big O of f of n. This means that the linear function g of n grows slower than the cubic function. In other words, f of n will become the upper bound for g of n. To summarize, let's consider our third example. F of n equal to n squared plus 2n. This is a quadratic function. Now, let's explore how we can represent this function using big O notation. The first step here is to identify the dominant term in the function f of n. Here, the dominant term is n squared because n squared grows faster than n as n gets larger. So, we can say that f of n equal to big O of n squared. This indicates that the growth rate of f of n is primarily quadratic. Next, let's explore how we can represent f of n using the other big O notation. Cubic representation. We can say that f of n equal to big O of n cubed. This is also valid because n cube grows faster than n squared for large value of n. Therefore, f of n is also bounded above by n cube. Similarly, we can express f of n equal to big O of n the power of 4. Again, this is true since n4 grows even faster than n cube, so f of n is also bounded above by n the power of 4. Finally, we can say that f of n equal to big O of 2 the power of n. This is also correct because exponential functions grows faster than a polynomial function as n increases. Therefore, f of n is bounded above by 2 the power of n. In summary, we have analyzed the function f of n equal to n squared plus 2n and found that the most accurate representation is f of n equal to big O of n squared. We can represent it as big O of n cubed, big O of n the power of 4, and even big O of to the power of n. This example demonstrates how big O notation allows us to express the growth rate of functions in various ways, highlighting that while f of n is primarily quadratic, it can still be represented with higher growth functions. Let's observe the hierarchy of time complexities arranged from fastest to slowest. The first one is a constant time, which is the fastest time, and the last one is we have a factorial time, which is known as the most expensive time in class of time function. Here we have linear time. All the classes of time functions that reside on the right of linear functions in the complexity hierarchy serves as upper bound for it. This means that while a linear function grows at a steady rate, these higher complexity classes such as quadratic, cubic, exponential, and factorial indicate growth rate that exceed linear time. If you want a detailed explanation on the order of time functions, be sure to check out my YouTube lecture on time functions. It provides an in-depth look at these concepts. If you have any question about this example or big O notation in general, feel free to leave your comments in the comment section below.